The voltage fluctuations experienced in the office building violate ANSI C84.1-2011, which addresses electrical power systems and equipment. Specifically, the voltage regulation, which is the voltage change measured at the point of delivery to the user, should not exceed plus or minus 5% of the nominal system voltage. The voltage imbalance, measured as the maximum deviation from the average voltage of the three phases, should also not exceed 5%. In the described scenario, the voltage fluctuations range from 115.8 volts to 149.9 volts. Since the nominal voltage is 120 volts, a 5% variation would be 6 volts. Therefore, the acceptable range would be 114 volts to 126 volts. The observed voltage range far exceeds this limit, indicating a violation of the ANSI standard. The measured neutral to ground voltage of over 3 volts is also a cause for concern and likely violates established standards. The Institute of Electrical and Electronics Engineers, IEEE Standard 141, recommends that neutral to ground voltage should not exceed 5% of the line-to-line voltage. Considering a 208-volt line-to-line voltage, 5% of that would be 10.4 volts. The National Electrical Code, NEC Article 250.4, states that neutral to ground voltage should not exceed 2 volts. The observed 3 volts exceeds the NEC limit. Several factors can contribute to voltage fluctuations and high neutral to ground voltage. Firstly, overloaded transformers can cause voltage drops and instability. Secondly, poorly balanced loads across the phases of the electrical system can lead to uneven current distribution and voltage imbalances. Thirdly, loose connections in the wiring can create resistance, leading to voltage drops and fluctuations. Finally, grounding issues, such as improper grounding or ground faults, can cause elevated neutral to ground voltage. These conditions can have adverse effects on various electrical and electronic components. Sensitive electronic equipment, such as computers and medical devices, are susceptible to damage or malfunction due to voltage fluctuations. Lighting systems can experience flickering, reduced lifespan, or premature failure. Motor performance can be affected, leading to reduced efficiency, overheating, and potential damage. To address these issues, several actions can be taken. Firstly, it is important to contact the building supervisor again and inform them of the specific violations of ANSI C84.1-2011, IEEE Standard 141, and NEC Article 250.4. As well as the potential consequences of these violations. Secondly, request that the building supervisor initiate an investigation and correct the issues immediately. Thirdly, if the problem persists, consider contacting a qualified electrician or the local utility company for assistance in diagnosing and resolving the electrical problems. It is also advisable to maintain a log of voltage measurements and any other relevant data to support any complaints and document the extent of the problem. To elaborate further on the possible causes, consequences, and actions to take regarding voltage fluctuations and neutral to ground voltage issues, it's important to delve into the technical aspects and potential solutions. Overloaded transformers are a common culprit. Transformers are designed to operate within a specific load range. When the load exceeds the transformer's capacity, the voltage tends to drop. This is because the transformer's internal impedance causes a greater voltage drop as the current increases. This can be exacerbated by harmonics in the load current, which can cause additional heating and voltage distortion. To mitigate this, the transformer's load should be measured and compared to its kVA rating. If the load is consistently high, upgrading to a larger transformer might be necessary. Poorly balanced loads occur when the current drawn by each phase of a three-phase system is significantly different. This imbalance can cause voltage differences between the phases and an elevated neutral current. In a perfectly balanced system, the neutral current would be zero. However, in reality, imbalances are common, especially in office buildings where single-phase loads like computers, lighting, and small appliances are unevenly distributed. To correct this, load should be redistributed as evenly as possible across the three phases. This may involve moving circuits, reconfiguring panels, or installing additional circuits to balance the load. Regular load audits can help identify and address imbalances. Loose connections are another frequent cause of voltage problems. Over time, connections can loosen due to vibration, thermal expansion and contraction, or corrosion. Loose connections increase resistance, which leads to voltage drops, heat generation, and potentially arcing. This can create intermittent voltage fluctuations and, in severe cases, pose a fire hazard. A thorough inspection of all electrical connections, including those at the transformer, panel boards, circuit breakers, and outlets, should be performed. Any loose connections should be tightened, and corroded connections should be cleaned or replaced. Infrared thermography can be used to identify hotspots caused by loose connections. Grounding issues can manifest in various ways, leading to elevated neutral to ground voltage. A properly grounded system provides a low impedance path for fault currents to return to the source, which helps to quickly trip circuit breakers and protect equipment. However, if the grounding system is compromised, fault currents may take unintended paths, causing voltage drops and elevated neutral to ground voltage. Common grounding problems include corroded ground connections, undersized ground conductors, and improper bonding of metallic components. The grounding system should be inspected to ensure that all connections are clean and tight, and that the ground conductors are of the correct size. The resistance of the grounding system should be measured to ensure that it is within acceptable limits, typically less than 5 ohms. The NEC provides detailed requirements for grounding and bonding. The consequences of voltage fluctuations and high neutral to ground voltage can be significant. Electronic equipment is particularly vulnerable. Voltage sags and swells can cause data corruption, hardware damage, and premature failure. Uninterruptible power supplies, UPSs, can provide temporary protection against voltage fluctuations, but they are not a long-term solution. Lighting systems can also be affected. Voltage sags can cause flickering, while voltage swells can shorten the lifespan of lamps and ballasts. Inefficient lighting can increase energy consumption and maintenance costs. Motors are also sensitive to voltage variations. Undervoltage can cause motors to draw more current, leading to overheating and reduced efficiency. Overvoltage can damage motor insulation and shorten its lifespan. Voltage imbalance can cause motors to run rough and overheat. Regular maintenance and monitoring of motor voltage and current can help detect and prevent problems. The actions to take should be prioritized based on the severity and urgency of the problem. Informing the building supervisor is the first step, but it's important to provide specific details and supporting data. A log of voltage measurements, along with any observations of equipment malfunctions or unusual behavior, can help demonstrate the extent of the problem. If the building supervisor does not take prompt action, it may be necessary to escalate the issue to higher management or to outside authorities. Contacting a qualified electrician or the local utility company is essential if the problem persists or if there are safety concerns. A qualified electrician can perform a thorough inspection of the electrical system, identify the root cause of the problem, and recommend appropriate solutions. The utility company can also provide assistance in diagnosing voltage problems and ensuring that the service voltage is within acceptable limits. In addition to the specific actions mentioned, there are several other steps that can be taken to improve the overall quality of the electrical system. Surge protection devices, SPDs, can protect equipment from voltage spikes caused by lightning or other transient events. Harmonic filters can reduce harmonic distortion caused by nonlinear loads. Power factor correction capacitors can improve the power factor and reduce losses in the electrical system. Regular maintenance and testing of electrical equipment can help identify and prevent problems before they become serious. ANSI C84.1-2011 provides guidelines for voltage quality and recommends that electrical systems be designed and operated to maintain voltage within specified limits. IEEE Standard 519 provides guidelines for harmonic control in electrical power systems. The NEC provides detailed requirements for electrical installations, including grounding, bonding, and overcurrent protection. By following these standards and best practices, it is possible to maintain a safe and reliable electrical system that provides clean and stable power to all equipment. Also, the investigation should include checking the connections at the transformer that supplies the building. Poor connections can result in voltage drops and imbalances. The utility company should also be involved to verify that the voltage at the transformer is within acceptable limits. Monitoring the voltage over time can provide valuable insights into the nature of the problem. Data loggers can be used to record voltage levels at various points in the electrical system. This data can be analyzed to identify patterns, trends, and anomalies. Also, it's essential to understand the building's electrical system configuration. Reviewing the electrical drawings and schematics can help identify potential problem areas. It is important to verify that the wiring is correctly sized for the loads and that the circuit breakers are properly rated. Another important consideration is the age of the electrical system. Older electrical systems may have deteriorated insulation, corroded connections, and outdated components. Upgrading the electrical system may be necessary to improve reliability and safety. Furthermore, energy audits can help identify opportunities to reduce energy consumption and improve the efficiency of the electrical system. This can include upgrading lighting systems, installing energy-efficient appliances, and optimizing HVAC systems. Load shedding can be used to reduce the peak demand in the electrical system. This involves automatically disconnecting non-essential loads during periods of high demand. In summary, addressing voltage fluctuations and high neutral to ground voltage requires a systematic approach that includes identifying the causes, assessing the consequences, and taking appropriate actions. By following established standards and best practices, it is possible to maintain a safe and reliable electrical system that provides clean and stable power to all equipment.